Alright, now let's check out some important operations. The first one is find mean. For any priority queue, there are several key functions to be considered, right? Like insertion, deletion, merge. Basically, they are all merge, right? But find mean is not supposed to be a problem for an ordinary min heap, because for an ordinary min heap, we know that there is only one tree and there's only one node, and that node must contain the smallest key. So find mean is trivial, we just find the root. However, in a binomial queue, we are having a forest of trees instead of just one tree. Therefore, find mean is no longer trivial. But the solution is quite simple. We know for sure that the minimum key must be in one of the roots. And therefore, we only have to scan every root and find the smallest key. That's how we do with find min, right? You might ask, why don't we just sort the roots and call binary search? Well, sorting the roots will make everything else more complicated. Okay, so the simple solution is just to scan all the roots. So the complexity, the time complexity depends on the number of roots. So if we have totally n nodes in the queue, and there must be at most how many roots? Think about it. It's the same question as to ask, given any integer n, if we rewrite this integer n in its binary form, how many bits do we need to store this n, right? The number of bits in the binary form of n is the same as the number of roots in this binomial queue with n nodes. So what is that number? Log n, right? And therefore, the time complexity in the worst case is log n. So it takes log n time to find min. And another way to do this is that we can remember the minimum and update whenever it is changed. Then this operation will take only a constant time. What does it mean? That means we can take some extra space to use another variable to simply store the minimum key and its position. So anytime when your user asks you to find min, you just return that minimum key. However, I don't think it actually matters because in most of the applications that will require us to use a priority queue, the most commonly used operation must be delete min, right? That's basically the whole point of using a priority queue, is when people want to get the minimum element frequently. So if the most commonly used operation is delete min instead of find min, what's going to happen with this implementation? We can take a constant time to find min, alright? But after deleting that minimum key, we'll have to update it, right? And this update will still take log n time. So there's no big deal. Alright, the next important operation is merge. Now let's take a look at this example. Suppose we have two heaps and we want to merge them into one. What must we do? Just look at them. Does it remind you of anything? Well, I said that the forest form of a binomial queue is closely related to the binary form of an integer, right? So it's like merging the two binomial queues is very much similar to the way we add two binary numbers. So when adding two binary numbers, what do? We start from the zeros bit, right? And this is 0 plus 1, and we get 1. And which means here, there's an empty tree plus a one node tree, so we just copy this tree down to the result. Alright, so the next bit is 1 plus 1. What do we get? We get 0 at this bit plus another 1 carried over to the next bit. right? So what does it mean here? It means, so 1 plus 1 means we have two b sub 1s, and let's merge them and carry it over to the next position and keep this position empty. Okay, so that corresponds to the 0. It's a null pointer here. Okay, and at the next position we have 1 plus 1 plus another 1. So what do we get? We get 1 plus something else, just carry it over to the next position, right? Okay, so here we have several options. We can merge any two of them and carry the result over to the next position and keep one tree at the current position. All right, so here I would prefer to merge these two trees and carry it over to the next position and keep this one at the current position. And we check the last one. There's nothing, means 0 plus 0 plus 1 carry. So here we are. One detail to be noticed here is that when we are merging two trees, we must make sure that the root is the one that contains the smaller number. Okay, so we are attaching the larger root to the smaller root and to make sure it's a min heap. So when we write the program, what we do is that we are merging into heap 1, and after merging we're supposed to clean up H2. Okay, we set this binomial queue to be empty and return H1 as the result. So what is the time complexity of this merge? At each position, what we have done takes only a constant time, right? So it's big O of 1 at each position, and therefore the time complexity depends on the number of positions, the number of trees we have. So what is the maximum number of trees? Log n, right? But be careful here. In order to guarantee that we can have it done in log n time, we must make sure that this merging process goes from the lower bit to the higher bit in order, and therefore we must keep the trees in the binomial queue sorted by height, not by their keys. That's why we wouldn't sort all the roots and call binary search to find min. Alright, the trees must be sorted, alright, but sorted by their heights, not by the root keys. Okay, the next one is about insertion. Insertion is only a special case for merging, so there's nothing more to say. What's interesting is to see how we're supposed to insert a sequence of keys one by one into an initially empty queue. What is the total time? We know that if we do the same thing with an ordinary heap, the total time is going to be big O of n. So now with binomial queue, can it still be big O of n? Let's check out. Well, first, when 1 comes in, it's very simple. We just create a new node. Okay. When 2 comes in, we must create a new node and link them together. So it takes 2 steps. It's more expensive than inserting 1, right? But when 2 is inserted, the first position is open, and therefore the next insertion is cheap. It takes only 1 step to insert 3. This is the good case. So 1 and 3 are the good cases. 2 is a bad case, and 4 is an even worse case. Right? When we insert 4, we need to create 1 node and then make 2 links. Right? So the total step is 3. After 4, after this bad case, 5 will be another good case. It takes only 1 step, right? And we start it all over again. We get 6 takes 2 steps, and then 7 takes 1 step only. So what is the pattern here? It's this. if the smallest non-existent binomial tree is b sub I, then the time complexity of making one insertion must be a constant times I plus 1. So for example, if b sub 0 is empty, next time when we make the insertion, we need 0 plus 1, that is one step to create this one, right? And if we have one node here, and if this position is empty, and when we insert another node, it's going to take one creation of the new node plus one link and carry it over to this position. So it's going to take two steps when b sub 1 is missing. So it's going to be 1 plus 1, two steps. Okay? And then we're going to see that performing n insertions on an initially empty binomial Q will take a linear worst case time. And therefore, the average time is constant. It's not so clear at this moment, but later on we're going to see. We're going to try to prove this conclusion. So one of the most important operations is delete min. And this is also the most complicated operation with a binomial Q. Let's see how we are supposed to do it. Suppose this is the binomial Q we have. And now the user will ask you to delete min. So first of all, we have to find min, right? Find the minimum key at some position. So in this case, it's here. Okay, so 12 is the one that is supposed to be deleted. So step 2. First, let's remove this tree from the original binomial Q, and then create another heap that contains only the remaining trees. And then step 3, let's remove the root from this tree. Then after this root is removed, we're supposed to obtain 3 subtrees, right? And put these 3 subtrees together, we obtain another binomial Q, because each subtree must be a binomial tree, right? So let's remove the root and therefore obtain another binomial Q. Then what do we do next? Obviously, we should simply merge them, right? So last step is to merge these two binomial Qs and obtain this result. All right, so what is the total time complexity? Let's check these 4 steps one by one. With find min, we can have it done in log n time. All right, to remove this tree from the forest, it's relatively simple because after calling find min, we already know the position of this root, and we can simply set this pointer to be a null pointer. So it means that this tree is gone. Okay, so it takes a constant time to remove the tree. Now to remove the root from this tree and then generate another binomial Q, how can we do that? It's like free the space occupied by this node and then assign each subtree to the corresponding position of a new heap, right? So the time complexity depends on the number of children that this node has, right? So what is the number of children for b sub k? It's k, right? So what is the worst case of this k? Log n, right? In the worst case, b sub k can be the largest tree in the forest, right? And that k can be as large as log n. Now to merge, we have already analyzed that the complexity is supposed to be log n. So put them all together, the overall complexity would be log n.